This is a warm-up I want to make sure that we understand clearly. It's got a lot of important details in it, and I'm going to go over it with you with a full, complete explanation, and then I'm also going to show you a shortcut on how to actually use what's something called extreme reasoning to answer this question. But you need to pay attention to the first part because it's going to draw together a lot of what we've learned in hopefully an easy to understand manner. So please try to listen to the whole video. Consider the three situations below, labeled A, B, and C, ignore friction, and they want you to say, rank order the tensions between A, B, and C. So let's sort of break this. Let's first take a look at A. Now A is in equilibrium. It happens to be the only one in equilibrium, and there's really only one net force acting on it. So if we were to draw the free body diagram from A, we'd have a 2 kilogram mass, that is a force going down, which is the gravity force, which would be mass hanging times gravity. And there'd be a force going up, which is the force tension of A. Okay, well let's do sum of the forces in the Y for A. We're going to have mass of the hanging times A, the hanging mass times A, equals 0. Remember, this is the one that's equilibrium. So what are the two forces we're going to have? Well, I chose down to be positive, but it didn't matter because it's an equilibrium. The mass hanging times G minus force tension A. So force tension A equals mass hanging times G, which equals 2 kilograms times 10 meters per second squared, which equals 20 newtons. Now that's the maximum tension force you can have with the weights that we are given, because the force that's going to cause any tension obviously is going to be that 2 kilogram force going down. Now, what about B and C? Well, B and C must have less tension force than A. Well, why? Because they are going to have a net force, and that net force, in a sense, is going to take away from the tension force. Let me show you what I mean. Let's look at B first. We're going to treat B like a system. Imagine you did the system schema, that thing we learned on the free body diagram notes, and instead of circling either the 1 kilogram block on the table or the 2 kilogram hanging block, you circled both of them. You are now only interested in forces that are external, that pierce the dotted line. Well, if you look at it, the tension force is not going to be external. It's an internal force, so we can ignore it. We don't care about the tension force. So I can do, and for block C, for part C, you can do the same thing. Instead of circling them individually, you circle them together, and you're only interested in the external force. So sum of the forces of the system is going to be the mass of the system times the acceleration of the system, which will equal the hanging mass times gravity, because that is the only external force that pierces the dotted line that is causing motion, because that's what we're doing the sum of the forces for, the ones that cause motion. Okay, so if I can find the acceleration of the system, I would simply do the hanging mass divided by the mass of the system. Well, that's well and dandy, but why does the acceleration of the system matter? Because the acceleration of the system is also the acceleration of each individual piece. Think about it this way. If you were running with a ball and you had it in your arms holding it, the acceleration you had would be the same as the acceleration of the ball, which would be the exact same acceleration as you holding the ball. They'd all be the same value. So this way we can actually figure out the acceleration of each individual block simply by finding the acceleration of the system. The ball couldn't be accelerating faster than you or vice versa. That wouldn't make any sense. But notice this equation. It should look somewhat familiar. You should glean that it actually is an equation you learned in notes, but more specifically, the pulley investigation. The pulley investigation, you actually found the acceleration of the system. And what you end up finding is the acceleration of the system for an Atwood machine is the difference in the forces causing the motion divided by all the masses added up together, or the mass of the system. In this case, there's only one force that's causing motion. That's the gravity force of that 2 kilogram hanging block. Now on the Atwood machine in the investigation, you had two forces. So you would have the difference between those two hanging masses divided by the masses added up underneath. In one of the modified Atwood machines, which we did some example problems with, where it was on a ramp, you had the difference between the hanging mass gravity force and the component of the hanging mass force of the mass that was on the ramp that was causing motion. So again, the top, or the numerator, of an Atwood machine acceleration equation is going to be the difference in those forces divided by all of the masses. So let's take a look at block or system B. So system B, the acceleration of the system, is going to be the hanging mass, because that's the only force acting that's causing motion, and the mass of system B. So I'm simply going to have that same 2 kilograms times 10 meters per second, which is 20, and then the 1 kilogram mass that's on the table, and then again that 2 kilogram mass that's hanging. So it's basically 10 divided by 3, and I get 6.7 meters per second squared. Okay, what about C? Well, C is the same exact equation with one difference, so to speak. You still have the 2 kilograms and the 10 causing the 20 newtons on top. But on bottom, you have 2 kilogram mass that's on the table plus the 2 kilogram hanging mass. So now I have 20 divided by 4, which is going to equal 5 meters per second squared. Now this is all well and good, but it doesn't actually give you the force tension, because that's what you're looking for. Well, now that we have the acceleration of each individual system, let's look at the acceleration, or the force body, the free body diagram of the block that's on the table. If we look at block B, we have a 1 kilogram mass, but it only has one force going to the right, which is the tension force. Now, it is true, there is a force normal and a gravity force, but they equal each other, and they're not important to the motion of this block. Why? Because there's no friction. So they equal each other out, but they have no bearing on the motion of this block in that X direction. For block C, it's the exact same thing. We have a 2 kilogram mass this time, and now we have the force tension of C. Well, how does this help us? Well, think about your sum of the forces in the X direction. In the X direction, all you're going to have is the mass times the acceleration of the system, because we know it's not in equilibrium, which is going to equal your force tension. So let's look at the force tension for B. The force tension for B is going to be the mass of B times that same acceleration of the system. So the mass is 1 kilogram, that's the mass of B on the table, times 6.7 meters per second squared equals 6.7 newtons. So the force tension on C is going to be the mass of C times the acceleration of the system, which is 2 times 5, which is going to equal 10 newtons. So now you know that the largest one, which is A, is 20 newtons. The second largest one, or the middle one, is C, which is 10 newtons, and the smallest force tension is the 6.7 newtons. And like I said before, you're going to have a larger net force on B, which is going to, in a sense, take away from the tension force, which you can see here. So what is the answer? Well, the smallest is B, then C, then A. But there's even simpler way to actually do this. Let's do extreme case reasoning. Now you have to realize, hopefully, that this 20 Newton force is going to be the maximum one that you could have. And if you can make that realization in this problem, this extreme case reasoning works. And what extreme case reasoning means is you have a difference, you make the difference much larger. So let's think about it. What if I change the 1 kilogram, which is the smaller one, to say, I don't know, 1 gram? And what if I took the largest one, which is 2 kilograms, and made it, say, 2,000 kilograms? Now just think, as far as when you're doing extreme reasoning, you're not getting quantitative values, you're getting qualitative values. So if I was to pull on B, would it take a lot of tension to move B? No. Compared to C, especially not. I'd really need to pull C very hard to get it moving, but I wouldn't have to pull that hard for B. So C is going to be larger than B. And if you realize that A is the largest, that makes answering this question very, very simple. So that's extreme case reasoning, and I always recommend it, especially for qualitative reasoning, because it makes a lot more sense and you can easily see it. Now, if you want to read what I basically just said, all of it is typed out right here. So you can pause it and read that if you need some more explanation. But let's get back to the question. So the question is, again, which one was the smallest, and which one was middle, and which was the largest? Or which one matches what the scenario is here? Well, C was the middle one, B was the smallest, and A was the largest, which leads us to answer number 7. I hope that helps. Let me know if you have any questions.